Hello, my name is Samuel Sparger, and this is my Physics 2211 Lab 1 report on the constant velocity lab. In this report, I worked on and recorded and analyzed the motion of a marker rolling across a one-dimensional plane in order to measure at a constant speed. I used a tracker to help determine the position versus time data, and then I created a model and glow script that, based on the data I collected, in Newton's second law in order to compare the model and my current data. The main purpose of this lab was to test whether constant velocity and its motion can be predicted using a physics-based model and glow script. For the experiment, I recorded a marker rolling across the table in a straight line, and I analyzed the position versus the time of the marker using the tracker. By marking the position of each of the marker frame by frame, I was able to determine the object's position values along with its corresponding times. This lab mainly focuses on Newton's second law. The lab used the data collected to create a constant velocity model and glow script. The system in this lab experiment was the table, the marker, and the hand that pushed the marker. One error with this lab could possibly be that the marker was not moving at a constant velocity during the video frame, as it is hard to tell in real time. The lab relied on a couple of different physics principles. The main one was Newton's second law, which states that the force on an object causes acceleration. In the equation form, the velocity update can be written as V final is equal to V initial plus the net force divided by mass times delta D. The position update formula is another formula that I was using in this lab, which is R final equals R initial plus velocity times delta T plus 1/2 times net force over mass times delta T squared. One of the most important assumptions that was made during this lab is that the net force is equal to 0 or is approximately 0 when the marker is moving. This is because when the net force is 0, the acceleration is 0, which means the velocity stays constant, so the model should predict a straight line in a position versus time graph. Here we can see the tracker model that was used in order to determine the position versus time of the marker rolling across the table. On this tracker, we can see each position data point marked by a red diamond, and there are approximately 28 of them, as there are 28 frames in this video of the marker rolling across the table. Each frame then determines the time versus the position of the marker in order to analyze and give us data, which can be seen in the bottom right in the graph and in the top right in the chart form. This tracker was overall very useful in this lab for calculating the position versus time of the marker. It shows the computational model and glow script that was used in order to simulate the position versus time. I used a lab 1 starter code with a couple minor changes. The biggest change was changing the net force to be equal to 0 in the simulation. I also set the initial position of the ball to be 0, 0, 0, which is the origin. Finally, I set the initial velocity to about 0.42 meters per second in the positive x direction. I also set the time step of delta t equal to 0.033 seconds, which matches about 30 frames per second. During the loop of the program, the velocity update happens first, and then the position update happens using the new velocity. Since the net force is equal to 0, the velocity does not change, and the object moves forward at a constant speed. This can be seen in the chart below, marked by the green line of the position versus time of the marker. Here we have a chart that depicts the predicted position versus the observed position. The predicted position is the glow script computational model, and the observed position is the actual tracker that was used to determine the position versus time. As we can see, the observed position is slightly higher than the predicted position, but overall it is not a huge difference. The other difference that we can see is that the predicted position, each data set always falls on the line of best fit, whereas the observed position has some slight variances due to maybe possibly not being at a constant speed or errors in tracking the marker. What if questions is what would happen if the x-axis in the tracker was flipped, meaning that positive x direction and negative x was swapped. If I flip the axis, the marker would appear to move in the opposite direction, so the position values would become negative instead of positive. The velocity would also change the sign, but it would have the same magnitude. This is because the speed would stay the same no matter which direction it is moving in. So the overall physics of this does not change. It would still be constant velocity motion. The only difference is the direction in which the marker was rolling. This lab mean. This lab means that when the net force is equal to 0, all of the different forces end up canceling each other out, meaning that meaning that the constant velocity is a result of this. For example, gravity pulls downward and the normal force of the table pushes upward, so these two cancels out, meaning displaying the constant velocity in motion that was seen in this lab.